Okay, here we go with 7.4. We're going to look at the central limit theorem for proportions. Going to construct a sampling distribution for a sample proportion and use the central limit theorem to compute probabilities for sample proportions. First, let's look at constructing a sampling distribution for a sample proportion. In a population, the proportion who have a certain characteristic is called a population proportion. The population proportion is denoted by P. In a simple random sample of n individuals, let X be the number in the sample having the characteristic. The sample proportion is P hat. We call this P hat equals X divided by N. So, computer retailer wants to estimate the proportion of people in her city who own laptop computers. She cannot survey everyone in the city, so she draws a sample of 100 people and surveys them. It turns out that 35 out of the 100 people in the sample own laptops. So the sample proportion, P hat, is 35 over 100. The proportion of people in the entire city who owns a laptop of the population proportion, P. So several samples can be drawn from the population like we looked at in the last section. They're very likely to have different values of P hat because obviously before we said they're very likely to have different values for the mean. So each time a sample is drawn, P hat is a random variable. Remember, a random variable is a variable that has a numerical value, and it has a probability distribution. The probability distribution of P hat is called the sampling distribution of P hat. So consider tossing a fair coin 5 times. This produces a sample size n equals 5. Where each item in a sample is either a head or a tail, the proportion of times the coin lands on heads is the sample proportion P hat. The probability that it lands heads each time is 1/2, as we know. Therefore, the proportion population of heads is also going to be 1/2. Next, we're going to look at all 32 possible samples that can be constructed. Here we go. So the table displays all the possible values of a size 5 and their sample proportion P hat. The mean of all the values of P hat is mean of P hat is 0.5 and the standard deviation values of P hat is standard deviation P hat as 0.2236. So next we're going to compare these values to the population proportion 0.5 and size 5. Now again, I just want to look at here, these are all the possible ways that we can have heads or tails, and that is with 5 times. In a previous table, the mean of the sampling distribution we said is the mean of P hat 0.5. It's the same as the population proportion 0.5. This relation, once again, always holds. So the mean of the sampling distribution of P hat is denoted by U mu of P hat and equals to the population proportion. The standard deviation of the sampling distribution is little sigma of P hat 0.2236. It is not immediately obvious how this is related to the population proportion and the sample size. However, if you take your mean value and you multiply it by its complement and then you divide it over how many times you're taking your sample, then you will get your sampling or your standard deviation of P hat. So the standard deviation of the sampling distribution of P hat is denoted by, again, the square root P times its complement divided by N. Now, if we take a look at soft drink cups at a certain fast food restaurant, have tickets attached to them. Customers peel off their tickets to see whether they win a prize. I don't know if they still do that. They used to. The proportion of tickets that are winners is P equals 0.25. A total of 70 people purchase soft drinks between noon and 1 on a certain day. Let P hat be the proportion that win a prize. Find the mean and the standard deviation of P hat. So the population proportion is 0.25 and the sample size is 70. So the mean is going to also be 0.25 because we have the population proportion. The standard deviation is going to be that 0.25 times 0.75 divided by 70 and take the square root of that, and you will get your standard deviation of P hat of 0.518. Looking at a probability histogram for the sampling distribution of P hat for the proportion of heads in 5 tosses of a fair coin is presented. We can see that the distribution is reasonably well approximated by a normal curve. The experiment is conducted again, but with 50 tosses of a fair coin. As we increase the number of tosses of the sampling distribution, P hat becomes closely approximated to the normal curve. Now, remember before, we said if it's under 5, if it's already approximately normal, it will still work. And they're just showing you here that if you increased it, it would fit even better by a normal curve. So when P is 0.5, the sampling distribution is somewhat close to normal, even for a small sample 5 like n equals 5. But when P is close to 0 or close to 1, you'll need a larger sampling size to get that closer to normal. And we talked about that in the last section. So if you don't know if it's normal, then you're going to have to go with something that's larger than 30. A common rule of thumb is that a distribution may be approximately normal whenever n times p and n times 1 minus p are both at least 10. So let P be the sample proportion for a sample size n from a population with population proportion P. If n times P is greater than or equal to 10 and n times the complement is greater than or equal to 10, then the proportion of P hat is approximately normal with the mean mu P hat equaling the proportion. And the standard deviation would be little sigma of P hat, the square root of P times 1 minus P all over n. Now if we look at a sample size of 20, drawn from the population proportion of 0.7, is it appropriate to use a normal distribution? Okay, so we have our sample size of 20, we have our population proportion of 0.7, we multiply these two together. Let's take a look. We get 14. And if we take n minus 1.3, which is 20 times 0.3, we get 6. But this is not at least 10. So we really cannot be certain that the distribution is approximately normal here because one of them is bigger than 10, but the other one is not. Let's look at a sample size of 55 drawn from a population proportion of 0.8. Is it appropriate to use a normal distribution to find probabilities for P hat? Yes, it is. N times P is going to be 44. N times 1 minus P is going to be 11. So both are at least 10. Then the distribution is approximately normal. All right, objective 2, let's use the central limit theorem to compute probabilities for sample proportions. According to a Harris poll, chocolate is a favorite ice cream flavor for 27% of Americans. If a sample of 100 Americans were taken, what's the probability that the sample proportion of those who prefer chocolate is greater than 0.3? All right, let's check the assumptions. N times P is going to be 27, which is greater than 10. n times p minus 1 is going to be 73.2, which is greater than 10, so we're good. We can use a normal curve. So now we compute our mu p hat and our standard deviation p hat. Our mu p hat we know is the same as p, which is 0.27, so that's done. And our standard deviation p hat is the square root of p times its complement divided by n. So when we do that, we get 0.44396. So find the area under the normal curve using the tables or technology. The probability that the sample proportion of those who prefer chocolate greater than 0.3 will be 0.2496. Here you go. Here's 0.3. You have your upper bound, 1 and 99 zeros. You have your 0.27 as your mean. And you have your standard deviation, 0.044396. Approximately 60% of eligible voters voted in the 2016 U.S. presidential election. If a sample of 88 eligible voters were polled, it would be unusual if less than half have voted. Okay, let's see. First, we check the assumptions. 88 times 0.6, yep, bigger than 10. N times 1 minus p would be 35.2, also greater than 10, so we can use the normal curve. We know that the mean is going to be the same, and the standard deviation would be that 0.6 times 0.4 divided by 88. We will get 0.052223. So we're looking at the lower bound of negative 1.99 zeros, and we have 0.5 as our upper value we just got here. 0.6 is our mean value, and 0.52223 is our standard deviation. Okay? We're looking at less than half. That's where this is. Okay. Oh, guess what? We are done. Notation for sample and population proportions, how to construct a sampling distribution for the sample proportion, how to find the mean and standard deviation usually using the sampling distribution of p-hat, how to use the central limit theorem for proportions to compute the probabilities for sample and proportions. Now, I don't have to tell you that you've learned a whole lot of stuff. And this day, only this day, not to mention the days before this. So once again, you're going to have to be well organized, take really good notes, and study this a bit each night so that you can keep these separated and know what to use when. Okay? Now, I will see you for the next day's lesson soon, and I will talk to you later.